Hey, hello everyone. Welcome to this SystemVerilog Scheduling Semantics session. In this session, we will understand how the SystemVerilog code gets simulated, right? And one might think that why do I need to understand? I am not going to be implementing a simulator. That is correct. We don't need to know all the intricate details of how the scheduling works, but as a users we need to understand the big picture of it, and and some of the what you say, the artifacts or the limitations of this particular algorithms through which the SystemVerilog simulator simulate the SystemVerilog, in order to understand why do we need to follow some coding guidelines, right? Like for example, the popular one is, we would have heard so many times, use non-blocking in your design, right? And why do we need to do that, right? That point may not be clear, and once we go through this SystemVerilog scheduling semantics, this particular point will become clear as to why do we need to use non-blocking. And then you might have heard about race condition, so all those aspects will become clear during this session. And in this session we are going to cover, we will first cover briefly, very briefly, as to like what does it mean to model the digital systems. This is not directly in the context of SystemVerilog itself, because when we say SystemVerilog, we rather look at it as HVL, which is high level verification language. But before we jump into it, we will look at it because it's also HDL, which is hardware description language. So mostly in the context of Verilog, we are primarily looking at it, because it's primary, the Verilog is part of SystemVerilog. So how do we model a digital system, and what does it mean to model it? And then how, once we understand that, then how does it exactly get modeled in the simulator, we will understand briefly. And then when we model it in the simulator, see, anywhere we are modeling from one domain to another domain, that is, we are trying to simulate a physical reality using the simulator. So there are going to be some limitations, right? We can't fully do it. Like even when you convert a analog signal into digital signal, that is, you are transforming from one domain to another domain, there is a loss, right? The same thing exists even in the simulator. So we will understand what is that, and then that loss or that artifact, one of the artifact is the race conditions. So we will look into few examples of race conditions, and then we will first look at the scheduling semantics of Verilog 2001, which is simpler. Why we are going to look into it is that the same concept gets extended and it becomes more complicated, right? More complicated in a way that, it's like, we can say, like, you have built a 1-bit adder and you instance multiple 1-bit adder to build a bigger, like a full adder, right? So similar way, the regions sort of are duplicated in a way. That's why it looks more complicated, but the crux of it remains same. So once you understand the fundamentals over here from the Verilog 2001, the same can be extended to SystemVerilog. So that is a reason why we will briefly look into it. And then when we go to SystemVerilog scheduling semantics, you will see there are more than dozen of scheduling regions, and it looks very complicated. But if we break it up and look at it more closely, there are only 3 categories. There are certain regions that are related to RTL simulations, or certain regions newly added for verification related regions, because predominantly the update to SystemVerilog from Verilog has taken place in terms of constructs that are added for verification. So to satisfy them, there are new regions added for the handling newer constructs that have been added in the SystemVerilog. And then we have the PLI based regions. So PLI is your Programmable Language Interface, through which you can interact with the C++ word using the Verilog or SystemVerilog. So there are some regions provided in order for a better integration with the PLI application. So we will look at it. So those are the 3 categories, and then fundamental concept of what we learn in the SystemVerilog, the scheduling semantics of Verilog 2001 extends to all these 3 regions. Our RTL almost remains same. We get some new regions which are sort of replica of what we are doing in the RTL for doing the verification, and then with some extension for the PLI. So we will look into those. So when we talk about modeling a digital system, right? So what I'm talking about is that you have built many combinational logic, you have built sequential logic. What if I look at a physical design and if I want to simulate it, what does it mean? That is what we are trying to understand, because ultimately what we want to understand is how does system Verilog gets simulated, and then what that means is what is system Verilog, and then system Verilog is part HDL and HVL. So as a part of HDL, what is happening? So in HDL we are trying to model the digital systems. So the digital systems consists of events. Events means, okay, something is changing, right? So there is a signal that is changing from 0 to 1 or 1 to 0, that is an event. And then those events have propagation delays, that when they go through the gates or when they go through your storage like flops, they have propagation delays. And then there are multiple of them operating at the same time, that each of the gate that you have in your design is operating concurrently, that it is running independently. It is not dependent on anything else. That you have an IC package that consists of 4 AND gates. Now you, and let's say those are 4 2 input AND gates, and all of them can be used at the same time simultaneously, right? It is not that when you are using one the other is not accessible. So all 4 of them are accessible, and that is what is called concurrency, right? And the second is we have waveforms and timing. Here we are referring to that you have some sort of a clock, then you have signals, then multiple signals are changing, there is a relation between the signals, something is repeating, then something has some relationship, that a particular change in one signal leads to change in another signal. So we have waveforms, and then there is timing associated with those particular waveforms, right? That something is coming after so many clock cycles, or something is asynchronous, something is synchronous. So there's a timing aspect associated with it. And then we have the signal values, right? And this is very true when we are modeling something that we interface with the very utilized when we interface with the external world. Then you can have a driver where you are driving weak, you are driving strong. It could be unconnected line modeling high impedance, and then there could be multiple signals driving something leading to unknown value. So there can be many things. So I mean many signal strengths that we could be modeling. So those comes under those needs to be modeled as well as a signal values. And then you have shared signals, that you could have a bidirectional bus as a simplest level, or you also have like a wired or a wired AND type of a network which needs to be modeled. Although the shared bus concept is I mean I'm not seeing that much in real usage, but it does exist. So maybe at the board level still do use it. Like for example, in the past, PCI not PCI, not PCI Express, the original PCI used to be a shared bus, but now the all the latest buses that are coming are all point to point. But I'm sure that still there might be some board level designs that are done where they could be using some shared signals. So that also needs to be modeled using the HDL. So these are the aspects of a digital system that needs to be modeled. And when we create a language that provides constructs for modeling all of these, there are two primary use cases. One is the simulation tools will use such descriptions for mimicking the physical system, because that's what we are modeling. And the model that is used behind such simulator is called discrete event simulation model. We will briefly look a bit more detail into what this means. And second is you could have synthesis tools which will synthesize such a high level description to a gate level descriptions. So there's the another use case for the hardware description languages. So among them, I want to emphasize a little bit on concurrency, because this is something that is the one that is a primary problem, right? So when we look at hardware design, you have multiple combinational and sequential logic, right? And all of them are concurrent. That is, they are all operational at the same time, and we can give different inputs, and they will provide different outputs at the same time independently, right? Because this happens because in real hardware, in the real silicon, as I talked about, like a 4 2 input AND gate package, they all have a physical existence, right? So they have their own real existence in silicon, and hence they are all operational at the same time, and any input that is given, they can generate the output. But when we want to simulate such a hardware on a processor based system, so what is the problem, right? That is what we should understand. So what happens is we just have a single processor. Okay, it could be multi-threaded, but at the same time, the number of threads cannot match the number of independent concurrent elements that we are trying to simulate. So that point of multi-threaded becomes moot over here. Still the point that remains is you have a single processor, and you have to now model the behavior of all your combinational and sequential logic, right? I could be saying it's a 100K gate equivalent type of a design. Now, all those 100K concurrent elements have to be simulated on a single processor. All right, how do we do it? That is the main problem that we need to solve when we have to simulate the HDL description. So the way simulator deals with modeling of these digital system is it thinks of a digital system as a set of events, discrete events, right? And let's say here on this, let's say we consider this circuit. So at 5 nanosecond, this particular signal goes from 0 to 1, and let's say this event leads to, at the same time, leads to a 1 to 0 transition over here, and at a 10 nanosecond, this point becomes from 1 to 0 transition, and at 15 nanosecond this point changes from 0 to 1 transition, right? So the way the simulator looks at it is, although all the elements are concurrent, it looks at it as a set of discrete events happening in a specific order, and that's what is shown over here, that we have a change of value 1 to value 2 at 5 nanosecond, and that leads to change of value 3 to value 4 at 10 nanosecond over here, and another value 5 to value 6 at 15 nanosecond. So we consider this, if we do these value transitions, then we are simulating this particular system, and we are taking into consideration all the concurrency that exists in this particular system. And the way simulators now work is they focus on like managing the event generation. That is, event generation means that if I given some sort of a stimuli over here, then this should translate to generation of this and this events, and this event should lead to this event, right? And that can happen if we do the processing of events in the correct order, right? And then we need to generate these events, and then we need to order them. Those are the two things. If we do it, then we can model the concurrency in the system. So this is the basic concept behind the simulators. Okay, so if we look further inside the simulator, so what happens is you have your SystemVerilog code, and then you will have a SystemVerilog compiler which compiles the SystemVerilog code, where it does parsing of your SystemVerilog code, and then it looks whether the code that you have written is as per the syntax requirements, and if there is something that is not in line, then it will flag the error, and those errors and the warnings that gets flagged, you should be able to see it in your generally a compile.log that gets generated. So you should be able to see that, and once it has been compiled successfully, then it moves to the simulation. So in the simulation, so while generally what happens is, while the compiling itself, if they are creating a standalone simulatable, in that the code required to implement this discrete event simulation handling is also included. So when you run it, that's the main process that's taking control, and that's scheduling your SystemVerilog code and helping execute it. And along with the discrete event simulation handling engine, your simulator will have a constraint solver. So when in the future, when we see the constraints construct in the language, that constraint solver, how that part is implemented as a part of your simulator. And then you will also have a functional coverage collector, you will have assertion engine, there will be more things I'm just listing few key aspects over here. So those will all be part of your simulator. In the current one, in the context of scheduling semantics, we are mainly focused on this discrete event simulation engine model, and that particular algorithm models like a two-step progression of time, right? It models the progression of time in a way two steps. So one, what it does is whenever any events is seen on the input, it evaluates all affected component at the current time, and based on those events it schedules the future events, right? And it schedules, so let's say at a 5 nanosecond a particular event has taken place, then it will evaluate all of them and schedule all subsequent events that need to take place. And let's say because of that, let's say we had some delay statements based assignments and some calculations, so we have next events scheduled at 10 nanosecond, 15 nanosecond, 20 nanoseconds. So because of the event in the current time step, many future events could get scheduled. Now after scheduling all the future events, what it does is the simulation time moves to the next immediate time step. So in this case it will move to, let's say, 10 nanosecond, because between 5 nanosecond to 10 nanosecond there aren't anything that's expected to change. And again it applies the change that was scheduled at 10 nanosecond and evaluates all the components that get affected by it and schedules more events. So this is the way simulation keeps progressing. So the key point that we need to remember is, for any input stimulus change, the simulator will model the generation of additional events after evaluating the components that we have modeled, and then it will manage those events. And manage the events means that it will order them in which order they need to execute. It will model the ordering of them, and then it will also take care of the progression of time, as I talked about that. Okay, 5 nanosecond, then next immediate is 10 nanosecond, then 15 nanosecond, and so on and so forth. It will model how the simulation time should progress. It won't progress linearly like 1 2 3 4 nanosecond. It will progress based on at which time step the events are present. Based on that it will keep progressing. So all that handling is the part of your discrete event simulation model. So in summary, how do we simulate the concurrency? We are just executing the discrete event simulation model, and this discrete event simulation model will take the input events into consideration. It will apply the input event to all the affected components and thereby lead to generation of any additional events that are possible, and it will serialize and process those particular events. So that's how it will model the concurrency and the system being simulated. And once we do this, right, there are two possible deviations that can result. One deviation is the time it takes to simulate the behavior will take longer time than the what it would have taken if it was an actual hardware. And second, there are possibilities, there are cases whenever we violate certain coding guidelines, that the behavior that we expected or that we modeled may not get simulated. So those are the two cases in which it will become different, and let's look at what each of these cases mean in detail. So let's look at these deviations. So the first deviation that we talked about was the time deviation. So in a real hardware, if design executed or design operated for 1 nanosecond, then it means that it just took 1 nanosecond of wall clock time. That is, if you put a stop timer and measure it how long it took, it really takes one nanosecond, a very obvious one. But the same design, when it is simulated for 1 nanosecond, right, then depending on the level of the abstraction that I am modeling, it can take a different amount of simulation time. What it means is that if I am doing a high level behavioral model, then it might just take 1 minute of wall clock time, right? Like for example, I might be doing a high level model called, let's say for a multiplier, I might be just saying C equal to A star B. That's a very high level model, and that might just take 1 minute to execute 1 nanosecond of the simulation. But the same thing, let's say I do it with the Booth's algorithm, and then it might take 1 hour because the level of detail has increased. The number of components that needs to be simulated have increased. So when I do the same implementation in the form of RTL, it will take much longer. And the same RTL, when it is synthesized, the total number of gates and flops, and let's say I have synthesized it to a particular technology, I have a netlist, but in that netlist, let's say I'm not even annotating any delays of the actual delays of the logic as well as the nets. I'm not annotating them. Then it might take 1 day to simulate, because now you can suddenly see the total number of components have increased, and it is taking longer. And then same thing, now I took a netlist and I actually did the place and route, and then I annotated all the delays. Then the same design might take 1 week of wall clock time to do the same 1 nanosecond simulation. So now, as you can see, with a level of detail, whereas the last stage, it is very close to actual implementation, right? So that we have the real gates and flops, we have did the place and route, so we have all. I mean, it is this the last stage, it has become more accurate, right? Rather, the first stage it was least accurate, the last stage it has become most accurate, and the delay has increased. Now if you try to understand why this happens, is because the more and more detailed the design, the more and more events will get generated. This is a very important point to note, that you have your so because any input change now needs to go through so many components, and not only that, it needs to go through the so many components. In the stage where we didn't have delay, we were just simulating a zero delay model, and now we have to also compute the delay, and the delays could be different, and that could lead to additional events at different points of time. So your list of the where you do the ordered list of events to execute, the total number of events that needs to process has increased, not only because you have so many components, but also now the components have different delay. So the total number of events that it needs to process, the algorithm needs to process, has increased. So the point to note is that as the more and more details you add to your design, the total time it takes to simulate increases, because it has to process more number of events. So in summary, the simulation time is maintained by simulators, and it is progressed based on the events that are scheduled. At the zero time, what happens is your initial block actually triggers your execution. I mean, it starts off the event generation, and then thereon, once the events start generating, like it could be either you're starting the clock generation, for example, right? And then based on the clock events and delays that are present in your design or in your own test benches, the further events get generated. And then if events are generated such that mostly in the zero delay models, there could be multiple events in the same slot, and they need to be serially ordered and executed by the simulator. And then after the events of a particular time slot are executed, the simulation advances to the next time slot. And there is one more point. This is a point that we are going to get more deeper into the simulation scheduling semantics, which is a main core, the problem or the core topic of this session, that each time slot gets executed as multiple regions, and then within each time slot there can be possible of multiple iterations. That is, some change led to another change, and there could be a zero delay interaction that can happen. So these time regions within a particular time step, what do I mean by that is, at 1 nanosecond there is some change that happens, and because of that change, let's say another change triggers. So then the same time step gets executed multiple times till the values are stabilized. Like for example, if I had a crisscrossed gate based flop implementation, then that the crisscross has to take place, the transfer of values, and that could lead to multiple iteration through a same time step before the values are stabilized. So that is possible. So we were looking at the deviations possible. So we talked that there were two types of deviations possible. One deviation is the time it takes to execute the model for the same duration at different abstraction, how that varies we saw. There's a second deviation that we talked about, where there's a deviation from expected behavior. And this deviation from expected behavior is a result of something called as race condition, which we will now go a bit deeper to understand. And race condition, we say that a race condition has taken place when there is an unexpected dependence on the relative timing or the ordering of events. That's when the race condition has taken place. and the term race originates from the fact that there are two signals trying to race each other to influence the output first, and whenever there is a race there could be different winners, and because of that the result can be different. And it is because of this problem that predominantly why the scheduling semantics have been defined. And so idea is we have this discrete event simulation model, and that model in few cases can fail, right? And then to prevent that failure, you have now introduced this concept of scheduling semantics. So that is the whole the big picture. So now what we will do is let's understand then, and let's understand how the scheduling semantics are done. And the point to note is that the scheduling semantics itself will not solve all the problem. It will solve bulk of it, but not solve all the problems. Additionally, what we have to do is we have to follow some coding guidelines as well. See, what happens is we have to look at the languages such as SystemVerilog or Verilog in both the HDLs and HVLs in the context of the domain that we are trying to solve, and we should not look at it as a general purpose programming language wherein we do whatever we feel like, and then it could result in an unexpected behavior. We always need to keep it in mind. If you are doing a design, it is very important that just knowing Verilog is not going to make you a good designer. You have to know the real design, real design in the sense like you have to understand the digital logic fundamentals, and you have to an extent you have to create that model in your mind and then transfer that model into a Verilog implementation in a form that is specified as per the coding guidelines. Then only your design has a high likelihood that it will simulate as per what you had intended. Not only that it will simulate, it will also synthesize as per what you had intended. And when you violate these, there are two things that can happen. One is it may not even simulate correctly, and second worser is that it may simulate correctly but it may not synthesize correctly. So that is one aspect that you have to keep in mind, and you have to apply that, and understanding the scheduling semantics to an extent will help you understand why some of the coding guidelines have been put in place, and if you see these type of issues in future, what to do about it. It will help you understand that. So let's understand this race condition. Race condition is actually a modeling artifact, right? In the real hardware, the race condition doesn't exist. It exists in the simulation world because we are modeling the real hardware using an algorithm. That is why this race condition comes into picture. And the race condition most commonly occurs when there are multiple processes. Okay, there are multiple processes, that is first factor, and second factor is they are trying to read and write a common variable, okay, and at the same synchronized to like a same event or a same event region, right? Those are the three things. So you have multiple processes, and you have they're trying to read or write a common variable, and third is they're trying to do it at the same event, right? Then when you do that, that's where the race condition will have a high chance of appearing. And why this appears is because when you have these multiple processes and you have this common resource, right? Between two processes you are trying to access a common resource, the order in which these two threads will operate, that cannot be guaranteed. That is the main problem. So when that happens, then if one process is trying to write, another process is trying to read, there is no way to know whether the process that is going to read, will it read a new value that has been updated or will it read a older value, right? And that confusion, that indeterminism is what is race, that we do not know who will win, right? That is why it's a race. Now, so it's a result. So if we summarize it, it's a results of assignments, some certain type of assignments or expressions which are scheduled for execution in the same time region. Okay, and we will understand more about what's the time region. And now, since when they are scheduled in the same time region, their order of execution is not guaranteed, and since their order is not guaranteed, the behavior that they produce could change over time to time, and this non-determinism is what is a race, and forms sort of the foundation for why we need the scheduling semantics. Okay, let's look at some examples of race conditions. So this is your read write or a write read type of a race condition. So I have an initial block and I have an always block, and now this clock generator, if assuming that if let's say always gets scheduled first, then the clock variable is not initialized, so it's not going to generate a correct type of a clock, right? So this is one type of a race condition, and second is write race condition. So what we are trying to do, there are two multiple processes and both are trying to update at the same event and they are trying to access the same variable, right? In all of these cases you can see that, right? So this is at the 0 time who is going to execute, here at the passage of the clock among these two. So now if the first always block executes and then subsequently the second always block executes, at the end of this passage processing it will be value will be 9, and if it is vice versa the value will become 2. So now we do not have the deterministic value available on this variable x. Same thing for the declaration and initial. Now if the declaration executes first at the 0 time and after that initial executes, the value will be 1, and if it is vice versa the value will become 0. So again we have indeterminism, that is a race. And let's say fork join, I have an event type of a variable, and what I'm trying to do is in 0 time like at the passage of the clock, and in the 0 time I am triggering, I'm launching two threads, although there is no begin and end, but it is still a block. So I'm triggering the event and I'm trying to capture the same event. So now depending on which thread among these two gets scheduled first, that is indeterministic, it could be this thread or this could be this thread. Just because this thread comes first in the fork block doesn't mean that the simulator will schedule it first. It could schedule this thread, or if we have multiple blocks that I have coded within the fork, any block could be scheduled first. There is no guarantee as to which one. The order in which I code have no implication on the order of scheduling. So now what can happen is that I might get triggering thread scheduled first, and then my second thread could get scheduled later, and then the event is missed. So at E will keep waiting for the event. Now if the second thread gets scheduled first and then I cause the trigger, then this event will be captured and then event caught will get displayed. So these are the various scenarios which actually demonstrate the what the race condition means. So this shows the scheduling semantics for the Verilog 2001. As we discussed, the core concepts will remain same. So let's understand what this picture is trying to tell us. So any time step that executes, or the time slot that executes, that we had talked about in the previous slides, wherein look, okay, at 5 nanosecond we executed, at 10 nanosecond we executed. So for as a response to the event, when we execute it, it executes in the form of these 4 steps. Okay, so let's understand what these steps mean. So in the active region, right? So and each of these are called as regions. So in the active region, what it does is it executes all the blocking assignments, right? With your simple equal to, all of them will be executed over here, right? All of them, right? And then this is an important point. So what will happen is the RHS of any expression, right? So if I have done A and that less than or equal to B plus C, let's say, so the RHS is B plus C. The B plus C will be evaluated in the active region, but note that the B plus C will be evaluated but will not be assigned to A. So only the evaluation will happen in the active region, and then any continuous assignment statement will be executed in the active region, and your dollar display will be executed in the active region. So what we are trying to do, I mean what the Verilog scheduling semantics is trying to do is group the set of statements that will be executed in different time regions. And the reason why that it needs to do that is, as we talked about, the motivation is to prevent that race conditions, and we will see how it prevents it. And if you look at any general programming language, and when at any point of time the code executes, it's all executing in a way in an active region. There is no other region, right? It's only in the Verilog, where we are modeling the HDL, we have to create the pipeline behaviors and the notion of concurrency, and that's where we need the concept of regions. So then there is a inactive region, and ideally you should not be using it. So any statements, that blocking assignments that you do with the #0 is executed in the inactive region, and it's not recommended to do this. #0 is kind of hack. Now the next important region is this non-blocking assignment region. So this one executes. Now what happens is that a non-blocking assignment b plus c, what we had talked about, we had evaluated the value of b plus c in the active region. The evaluated value will be assigned to a when it comes to a non-blocking region execution. So that's what happens in the non-blocking assignment. And then there is a postponed region. In the postponed region, your $monitor or a $strobe type of commands will get executed. So overall what's happening, so you have a similar type of a time slot execution in the previous time slot. So at 5 nanosecond we would have executed, and after 5 nanosecond the simulator would have figured out that I have the next event to execute only at the 10 nanosecond, and at 10 nanosecond your all affected blocking assignments will take place, and your RHS of NBAs will get evaluated. Any continuous assignments will take place, your dollar display will take place, and then it will move on to the inactive region execution where your #0 blocking assignments will take place. And in the NBA we would assign the LHS with the RHS value that we had evaluated in the active region, and then in the postponed region $monitor $strobe will take place. After executing this, it means that that particular time slot has executed to completion, and then it will move to the next time slot. So let's say it will move to the 15 nanosecond and continue repeat executing these time slots again, so as a region. So this is what happens in case of Verilog scheduling. And most important things, forget like about inactive and postponed. What you need to remember is there is an active region where all the blocking assignments are evaluated and assigned both. Whereas for the NBAs, evaluation of your RHS takes place in the active region and the assignment takes place in the NBA region. If you remember this as a key concept as a part of your scheduling semantics for Verilog, this is good enough to understand how you can prevent the race conditions, and that is the motivation behind understanding all of these scheduling semantics, because we are not going to implement the simulator but still understanding it, because we want to understand how to prevent the races and why we need to follow the coding guidelines. In order to understand that, we are understanding this, and for that active region and NBA region concept, that active region executing blocking, evaluating and assigning, whereas for the non-blocking, evaluation of RHS taking place in active, assignment taking place in NBA is the key concept to remember. So okay, these are some of the coding guidelines that if you follow, the results, your simulation and synthesis results are more likely to match your intent, and when you break them, then there can be potential deviation from what you had expected or intended to the behavior that you see, right? So for sequential logic, use non-blocking assignments. That's very simple. For latches, use non-blocking assignments. So in essence, what it is trying to say is wherever you are modeling the storage, use non-blocking assignments. And this is important because in storage you essentially have a pipeline, that is you have one flop, another flop, and the output of one flop stage is sampled by input of another flop stage. And in such modeling, what happens is if you use blocking, then as we saw in the previous slide, there is a non-determinism that whether the input of the second flop should be sampled first or should it be updated by the output of the first stage flop, right? That's a non-determinism that comes into play, and with the non-blocking assignments, that non-determinism will not be there. So for any storage modeling, you have to always use non-blocking assignments, because it guarantees that the older value will be sampled all the time deterministically. For combinational logic, use blocking statement, and this you should not be doing, but for some reason if you are mixing the sequential and combinational logic in the same always block, then even for the combinational logic you use the non-blocking assignment. So that's your guideline 4, and your guideline 5 is do not mix blocking and non-blocking assignments in the same always block. That's not a good idea. Do not do that. And the guideline 6 is do not make assignments to the same variable from more than one always block. So this can always lead to like as we talked about, the potential for race increases when you are trying to do multiple process assignment to a same variable at the same clocking event. It always creates a possibility of race condition, so do not do this. And then use $strobe to display values that have been assigned using non-blocking assignments, because then as we saw that the $display executes in the active region where the non-blocking assignment has not yet completed. So when you use the $strobe, it gets executed in the postponed region, and hence you will be able to see the latest values. And do not make use of #0 in the procedural assignment. Sometimes it's very tempting to prevent the race conditions using the #0, but it's not a permanent solution, and it will cause problems further down the line. So using #0 is without understanding what is happening is generally not recommended. So if you follow some of these coding guidelines, then your code is more likely to function as you intended. I would like to close this with one point, that the early stages of Verilog, if you look at it, they didn't really have a non-blocking assignments, and there was only blocking assignment that was supported, and people were able to model both. Then the designer took additional care to make sure that the synthesis engines infer correctly. Non-blocking was only added as an additional thing. But using the non-blocking and using the blocking appropriately for each one of these makes sure that there is no confusion in the way the code gets simulated or synthesized. There are different form of race conditions, and here let's look at read write or a write read type of a race condition, right? And what we are doing over here is, we had seen this particular circuit, and to understand that, should we be updating this output or should we be sampling this input, right? And what happens if there is a difference in the ordering of doing those actions. We were trying to understand that. Now let's say if I model this particular circuit in this way, that is, at always passage of clock, I have this always block 1 where I'm saying x equal to 2, and again I have always at passage of clock, and I have an always block 2, and I am just saying y equal to x, right? So I am doing this now. How does this work, right? Now when according to the LRM, now when we have these two always blocks, we know that both of these could be scheduled in any order, right? The ordering of the execution of the always blocks that we have, there is a indeterminism, right? There's no guaranteed order between them. So now if at the clock edge 1, if the execution order happens to be the always block 1 followed by always block 2, then what will happen is the value of x would get sampled to be 2, and then the same, because it's a blocking assignment I'm doing over here, the value of x will be available, and then y equal to x, so the value of y I'm going to see is 2. So this is the output I will see, whereas according to my modeling, I was expecting, if I were to model this hardware, this is the behavior that I was expecting, and this is the behavior that I am getting, right? Now again, at the same time, if the so there is this difference of output that is happening. That is one problem. The second problem is that on the same clock edge, if the ordering suppose happened that A2 executed first and then A1 executed, then the y will sample the previous value of x, which would be 0, and then x will still get a latest value, which will become 2, right? Now even if I forget this specification for a moment, there is a difference that depending on the order of execution of these two always blocks, the output result that I am going to see can be different, right? And this is the this indeterminism is nothing but the race condition. So this is what is the problem of race. So if we revisit back the same example, and let's say this is the way we had modeled using the blocking assignments, and the top table is what we were expecting as a hardware behavior. And let's say now if I change from this left side to the right side, right, that is from the blocking I am changing it to the non-blocking. Now what happens, right? So now the in the particular time step when the passage of clock takes place, right, at that moment we are going to execute all the time steps that we talked about. So in the active region of this passage of the clock, the value 2, right, gets sampled and gets scheduled for the assignment in NBA region for the variable x. It's not assigned, but it's just sampled and scheduled, right? And in the while we execute this always block A2, again the value of x gets sampled, right? Now the value of x that we are sampling over here will be the previous value, and let's say if we are immediately coming out of post reset, the value of x would be 0. So we are sampling the value of 0 and scheduling it for assignment to the y. So in both the always blocks, any order they execute, right, we are not doing the assignment, right? We are just sampling the values. So what we will do, we will sample the value 2 in the active region and schedule it for assignment to the x, and we will sample the value of x over here, which will be currently 0 because this assignment has not taken place. We have just scheduled it to be assigned in NBA region, and while we are still executing it in the active region, so in the active region the current value of x would still be 0, let's say immediately out of the post reset, and that is what we are scheduling it for the y. So irrespective of the order in which this takes place, the value scheduled will remain same, and hence the behavior would be that on the clock edge 1 I will always guarantee to get this behavior, right, irrespective of the order in which they execute. Since we just sample it and we do not do the assignment, the value is guaranteed to be deterministic irrespective of the order of execution. Whereas in the blocking, since the value reflects depending on the order, because both the assignments are taking place in the active region itself. So if let's say x equal to 2 gets executed and then y equal to x gets executed, the y equal to x will see the latest value. Whereas if y equal to x gets executed first, then the y will end up sampling the previous value. But whereas in the case of non-blocking assignment, since we just sample and we don't schedule, and then the actual assignment and the actual assignment gets scheduled only in the NBA region, we will always sample the older value, and that's how the NBA region concept solves the race issue that we were seeing in the previous slide. So now that we have looked at how the Verilog scheduling semantics works, and we have also looked at some of the coding guidelines that we need to follow for HDL modeling, and we have understood what problem the Verilog scheduling semantics tried to solve. It tried to solve the modeling of storage and the how the race between like the assignments can happen in certain cases, and it helped to prevent that using the non-blocking assignments. Now when we come to system Verilog scheduling semantics, we had like about 4 regions in the Verilog, and in the system Verilog we have now about 17 ordered regions. So the time slot that we looked at in the Verilog, which had about 4 regions, now you have about 17 ordered regions, and 9 out of 17 right, are used for your system Verilog statements, and 8 out of 17 are used for the PLI code. Now these new regions have been introduced to prevent the race between RTL design and the new verification constructs that have been added. Right, it could be like assertions, it could be a clocking block. So to prevent the race between your Testbench code and even the program block, of course. So to prevent the race between your Testbench code as well as the design, the new regions have been introduced, and the PLIs, right? So it's a programmable logic interface. So what happens is you can integrate a C++ application to your verification word using PLIs. So through PLIs, you can call and pass information from Verilog or system Verilog word to a C++ word, and you can get information from C++ word to the Verilog word, right? So that's what you can do it with the PLI. So there have been these 8 regions that have been introduced, and that ensures that you can interact with the C++ application with more certainty, that exactly at what point the data is coming in and going out of the within the time slot, at what point you are able to. So that helps you sometimes modify or capture the values better in the PLI applications. Okay, so this is the scheduling semantics for the system Verilog. Don't get bogged down by the total number of steps that you see. We will divide them and make a sense out of it to make it meaningful for us to understand. Again, I would like to reiterate that we are not looking to implement this algorithm, right? We are looking at it from the point of view to understand it such that we can use the constructs properly. That's our intent. We are not interested in like understanding all the intricacies too. We are not the simulator implementers, right? But what we want to understand is that the intent behind them, so that we can use the constructs correctly. That's our goal. So the basic idea is same, that you have a previous time slot, and once the previous time slot completes, when you come to the current time slot, it goes through all these 17 regions to execute the current time slot. So that's the big idea, and then it goes to the next time slot. So there's a big picture, right? And in these 17 time slots, what we have is, we have marked the existing regions that we have borrowed from Verilog with this teal color. So we have active, inactive, NVA and postpone, right? So these 4 regions which we already looked at in the Verilog scheduling semantics, they are coming in same, right? There is no change, okay? And then the ones that are in the brown and the ones that are in the blue, right? Both of them have been added in the system Verilog, right? So the ones in the brown are newly added to handle the system Verilog constructs that have been added for the verification purpose, right? And the ones in the PLI, we will talk about it. So PLI is nothing but your programmable logic interface, and it's meant for your C++ applications to interact with the system Verilog world. That's what it is meant for. And I think, like, yeah, so the PLI usage is not very like not everyone generally uses the PLIs, but we will look into it. But our primary focus is on between this Verilog and system Verilog regions. Okay, so let's quickly jump into it. So we have these 3 levels of division anyway, and we know that active, inactive, NBA and postponed, right? What is the purpose of this? And in the active, we had all blocking statements executing, and then the RHS of the non-blocking getting evaluated. This is an important point. And in the NBA, the whatever we had for the non-blocking assignments, whatever we had evaluated on the RHS in the active region gets assigned to LHS. That's what happens, right? And of course, in the postponed, we are doing that $strobe and the displays of those. So that is what is happening with respect to Verilog. Now, for these 3 regions, right, which are the important regions of Verilog, they are mirrored in case of system Verilog in the form of reactive and reinactive and re-NBA. Now in the system Verilog, there is a construct called program block, and program block is equivalent to the module. Okay, module in Verilog is equivalent to a program block in system Verilog. And if you remember, we had used the program block for the FIFO test bench, right? Our entire verification code, we had put it in the program block, right? You should go look at it if you are not able to remember. Now, any blocking or non-blocking assignments that exist in the program block will execute over here. So the blocking assignments in the program block will get executed. That is, both the evaluation as well as assignment will happen in reactive region, and the RHS of non-blocking assignments of program block will get evaluated in the reactive region, and they would be assigned to their LHS in the re-NBA. That's all. So these 3 regions and these 3 regions are mirroring. And so what happens in a bigger picture level is that the RTL evaluates all its regions and its values, stabilizes, and then test bench gets chance to look at them and react to them. That's what. So the test bench is reacting to what the design is doing, and if we had put these also over here, then there was a possibility of race conditions that could have happened among these statements. So that is now not happening, right? So repeated re-triggering could have happened. So now that's not going to happen because we have separated them out. That's the first concept that we need to understand. The second concept that we need to understand is that in the system Verilog, there are two more constructs introduced called clocking block, and then that you will see in the subsequent sessions. There's a clocking block, and then there's a assertions that we have introduced. And both the assertions and clocking block, they use this preponed region. Okay, so clocking block samples its values in the preponed region, and it will we will see, you will see a lot more details about it in the when you learn more about clocking block. And assertions also sample the values that they are using in the preponed block, and whatever it has sampled, it will evaluate them in the observed region. Right, it will evaluate them in the observed region, and the results of that evaluation, there is a action block that gets executed, and that will get executed in the reactive region. So this is what happens with the assertions. Okay, so this is the big picture. Okay, this is the way you have to look at the scheduling regions. And then of course you have PLIs. So what the PLIs are trying to do is, PLIs are a way to, as I talked about, is a way to interface your C++ application to your system Verilog simulations that are running, and you want to make sure that you can pass the information from system Verilog word to your C++ word and bring the information from C++ word to the system Verilog. That is what is the interface of this PLI, right? PLIs are the portals through which you exchange information from system Verilog to C++, C++ to the system Verilog. Now there are various regions that are provided, and in these regions the exchange of information with the PLI can take place, right? And these regions help help provide a certainty that okay, I want to see the values before NBA, right? Or I want to see before execution, or I want to see after everything has executed. So this way the PLIs can interact more closely and implement various applications that are very close to the behavior of the simulator that we are trying to do. Like for example, we will see some, like, you could be dumping waveforms and you want to capture all the information that how the signal has transitioned. Sometimes the waveforms allows you to zoom into how this overall time step execution takes place, right? There's a delta cycle model we call, wherein in waveforms in some cases you can actually zoom in and look at how this whole transition has happened, and if that has to be captured, then we need hooks to capture those transitions, and that's where the PLIs come into play. But bulk of us, I think, like, we would be mostly focused on these active NBA, reactive re-NBA, preponed, and then observed and postponed. This is what we will really be concerned with. And then once the postponed concept remains almost the same, and then once that's executed, we go to the next time slot. In the next few slides, we will look little bit more detailed. I think the big picture has already been given out, and I have already talked about briefly about what each of these regions do, but we will summarize it in the next few slides. Okay, let's summarize the big picture first. So the regions, the way they are used: RTL functionality, active, inactive, NBA, verification functionality, as we already looked at it. So reactive regions, which are reactive, re-inactive, re-NBA, which are equivalent of this executing. So these are module functionalities, and these are executing in the context of program block. And we have the preponed region and the postponed regions, and the they are being utilized as a part of your, again, part of your like clocking block functionality. And the concurrent assertions, they utilize preponed region, observed region, and reactive regions. In the preponed, they sample the values; observed, they get evaluated; and the reactive is where the results, the action blocks that are action blocks saying that what should be done if an assertion passes or fails, is executed as a part of reactive region. And then I think, like, as we talked about the inactive regions, ideally you don't want to use it, so avoid using the #0 usage for the blocking statements. So now we will take a look at what each of the regions are doing. So let's look at Preponed Region. So in the Preponed Region, it's primarily used for sampling values for the concurrent assertions, as we talked about. You will learn in the context of concurrent assertions, we will refresh these concepts a little bit, but just take it on the face value that if I am building an expression, the values of the signals that are used in the expression, they are sampled from the concurrent assertions. Like for example, we talked about NBA, right? In the like a non-blocking, if I said A non-blocking assignment B plus C, then in the active region, I was evaluating the expression of B plus C and assigning it in case of NBA region. Same way, the values of B and C. So if I'm doing a concurrent assertion check on B and C, then the B and C values will be sampled in the preponed region, whereas whatever the expression that I'm forming and then the evaluation of that, everything will happen in the observed region. So that's what this statement means. So, and then there is a second construct, there's a clocking block which you will learn, and that also helps solve some of the race problems. So while doing that, you specify skews, and the input skew helps you to sample the signal. So when you say this is special way of specifying a time, so when you say $1 step, it samples the signal in the preponed region. So that's what is happening in the preponed region. And then preponed region is executed only once each time slot. It's a read-only region. There are no updates happening. And then simulator samples preponed region values, and it stores it and then makes it available in the later regions, right? Like for example, whenever the clocking event triggers, it makes it available. And preponed region is equivalent to sampling in the previous postponed region. So the previous postponed region as well as preponed, as you saw, there wasn't anything happening between them. So when we talk about clocking block, you will see $1 step, preponed region, postponed region, they are all equivalent. Okay, so we will talk more about it in the context of clocking block, but for all practical purpose, just remember this fact to avoid any confusion, that $1 step, preponed region, postponed region, they are all same in the context of clocking block. This is an important point, otherwise this always leads to confusion, so just remember this point. So let's look at the active region, which is made up of your active, inactive and NBA. So these anyway we have looked at in the context of Verilog as well. They are meant for scheduling your RTL and behavioral code activity. All your blocking statements, non-blocking statement, task or functions called, they all execute in the inactive region. This doesn't mean that you cannot put the Testbench code in a module, because we have already done that in the context of Verilog test benches. When we built, we have put that over there. As long as you use the right assignment types, it will still work. But only thing is that, yeah, you get better, what do you say, you are essentially reducing the probability, right? I mean, there's no 100% protection. I think as long as you use non-blocking assignments, you are kind of okay. Non-blocking assignments I'm talking about for interaction between your DUT and the test bench. As long as you use non-blocking assignments, even if the test bench code is written within the module, your stuff is going to work, right? So the program block was designed to place the test bench code separately. So it's just that. So whatever we wrote in a module for the test bench code, the same code you can just place it in the program block and instance it and use it, so that you can separate that out, and that's how it moves out of the active region execution. And then yeah, so to summarize it, so all module blocking assignments, evaluation of RHS of NBA, and then schedule them for assignment in NBA, and all module continuous assignment statements. Then even the Verilog primitives are execute within the active region. Then the $display and finish commands, they execute in the active region. Always block using blocking statement models. For the combinational logic, they also execute in the active region. I think like we have already touch based upon these concepts, were just reiterating them in the context of like summarizing them in the context of active region. Okay, so if you look at the inactive region, it's a part of your active region set. The #0 blocking assignments are scheduled. Then, like as we have already talked about it, #0 is not a good practice to use. So I think like yeah, that you have to take care. We are not going to go delve further into this area. Yeah. So the non-blocking events assignment region is again a part of your active region set. The main activity, I think this is what is a key point that you have to remember. The LHS of variable gets scheduled and updated, and all RTL clock logic is modeled using always block, should be coded with non-blocking assignments, and this ensures that they correctly function. They model the pipeline nature of the sequential assignments, right? So that is the primary goal of the non-blocking assignments. And observed region is a new region that was added for the system Verilog, and the main function is to evaluate the concurrent assertions. So you can imagine that assertions are important because like you know, a region has been allocated for them. So the values are sampled in preponed region and they evaluated in the observed region, and the action block of the assertion executes in the reactive region. So this is an important detail. Of course, we will refresh this a little bit in the context of assertions, but just remember this. And then you have the reactive region set. So reactive region set, as we have seen, it's mirroring or the dual of your active region set, and the principal function of this particular is sort of execute the equivalent statement in the context of program block, right? That's what it is. And then targets the scheduling of testbench stimulus and checking the same time slot after RTL has settled to at least a semi-steady state. So semi-steady because there is a possibility that the any combinational logic updates from the test bench can re-trigger the time slot again. That we saw that there is a possibility that it can go back. So that's why it's a semi-steady. And as we talked about, the test bench code could also be placed as a part of module code. It's not that the program block is must. And even with the program block, like there are cases where it is still not 100% guarantee that all the race conditions can be prevented. So the active region of your, the test bench, which is reactive, as we have seen, it executes your blocking assignments, and then the pass fail block statement for concurrent assertions execute over here. Your RHS of the non-blocking assignments get evaluated and get scheduled here, and then that whatever we have scheduled gets updated into NBA region, and then executes all program block, any continuous assignment that are present in the program block, and any like a $exit and implicit $exit commands due to some failures that are taking place are all happening in this reactive region. The re-inactive events region is a part of your reactive region set, and events scheduled in re-inactive region are the execution of #0 blocking statements that are present in the program block. Like we had said that we were like as a part of coding guideline, we didn't want to use the #0 blocking assignments in case of the RTL, but and that's why we didn't really bother to discuss the inactive region in depth. But re-inactive region can be used in verification code. It's not very frequently, but you have some cases where you can bring in the determinism for the verification code using the re-inactive region. It's an advanced concept, so we will probably little bit touch base when we talk about fork. So what happens is when you fork off the threads and you are launching multiple threads, the control first continues with the parent thread. Okay, the parent, unless the parent blocks, the control will not be passed to the child threads. But if at all you want to make sure for some reason that the child process gets a chance to execute before continuing parent, then what you can do is after fork, before you do the any of the, like let's say you're done a join none type of a thing, or a join, so yeah, especially the join none type of a thing, and you want the child process to execute, then you can put a #0 and that will ensure that the children of the 4 get a chance to execute, and then they will when they block every one of them blocks, and then the thread can continue with the parent. So under some special cases you can make use of it, but not something that you would want to use on your everyday programming requirements. Then re-NBA event region, I think we have now beaten this down to death, that the left hand side of the LHS gets updated, and this is for the LHS variables of the non-blocking assignment get executed in the context of the program block. And postponed region, as we have seen, it's primarily meant for executing your $strobe or $monitor. If you remember, we had used the $monitor in the context of the counter test bench, and that will show the updated values of the current time slot. Then this region actually in the context of SystemVerilog is also used for your functional coverage collection, and there is no feedback path from the postponed region back to RTL or like within whatever the reactive loop regions. So that's why the values displayed or the coverage collected will be the final values of this particular time slot, and after this it moves on to the next time slot. So let's briefly talk about the PLI region. This is a region where the PLI callbacks are scheduled. Callback means that you can, like whatever the registered functions that exist for C++ to exchange the value between your SystemVerilog word to the PLI word, they get called over here. And within the current time slot, the different regions, we can collect the information. And as we have talked about it, the PLI is a mechanism for C++ functions interaction with the Verilog code, and it's used for the passing of the data information, and then the objects in different, like the design hierarchy information can also be exchanged. This is the area by itself, and PLI is used for many applications. Some of them, like you're dumping waveforms, especially there are PLI calls that are being utilized for like FSDB dump, for example. You call a PLI call, and you will be able to see some of those when you do some of the I don't know. So yeah, when you use Wordy, you will be able to see that there are additional tools that you can also build in the future. So let's say you want to do some power analysis or like a memory modeling, fault injections. So these are some of the special areas in which the PLI gets utilized, and for those PLI regions are utilized. But I think for all practical purposes, we do not like really care about the PLI regions in our everyday working. Only on the special purpose is when you would really go deeper into this area. So that concludes the scheduling semantics for the SystemVerilog. And what you need to really remember, as we talked about, is the concept of your active region and the NBA, and how the blocking and non-blocking gets managed, and what are the new regions introduced in the SystemVerilog, and how the program block just mirrors the regions that we have done for the module, and the program block is a module equivalent in the verification word. And then for the concurrent assertions, remember how the preponed, observed, and the reactive region is used for its operation. So just remember those 3 regions, because when you go to assertions, you will probably re-encounter and you will need this information. And for the clocking block, just remember that $1 step, preponed, postponed, they are equivalent, and the $1 step is used for the clocking block. And for the functional coverage, the postponed region is used for the collecting information. And for each of these regions, there are those PLI based regions also included, which allow you to pass information to and fro from the C++ word. So I think broadly, if you remember these key concepts from the scheduling semantics, I think it is good enough. This is a area by itself again. So I think these key details are sufficient to perform your the verification test bench building activity. So yeah, this is one tricky area. I am not going to say it is simple, but at the same time, once you look at it from the perspective that has been described, and if you always keep that big level division in your mind, then it will be far simpler to understand and apply on the need basis. Okay, yeah, thank you for listening.